All right, so here is part 3, our Lewis structures for exceptions to that octet rule. So the first thing I want to go over as a big exception are when we have electron-deficient atoms. So these are ones that are going to have less than the 8. And we're focusing on beryllium and boron being the central atom that this will occur with. Sometimes we will see it make additional bonds than what we're going to see in these two cases if it's bonded to another species, but we'll get into that later on. So beryllium and boron should seem a little bit odd to you because beryllium and boron, we have a metal and a metalloid, but these do actually end up forming covalent bonds with certain nonmetals. So for this one here, when we do beryllium only has 2 valence electrons. Each chlorine has 7. So that's 14 and 2, so that gives me 16. You're going to start with beryllium in the center, still following the same rules. Okay, those are my chlorines. I'm going to draw single bonds to them, so that's 4, which means I have 12 left. So I'm going to go ahead and put my 6 and 6 on my 2 outer atoms. So that gets me to 0. Now, previously, you would have said, oh, well, let's start making double bonds. Well, with beryllium, it is an exception where you leave this alone as it is, and beryllium will only have those 4 electrons around it, and they find it that it's stable in this manner. Okay, so be on the lookout for beryllium. It's just when it bonds to our chlorines or sometimes hydrogens, we're going to see it just form these 2 bonds, and that's it. Okay, boron is going to have kind of a similar experience here where boron has our 3 valence electrons. I have 3 fluorines, they each have 7, so that's 21 and 3 electrons, which just gives me 24. I'm going to start with boron in the center. I'm going to put my fluorines around it. I'm going to start with my single bonds there, so that gives me 6, 2, 4, 6, which means I have 18 left. And if I look, I need 6 on each fluorine, so 6, 12, 18. There's my 18. So I'm going to go ahead and put those dots on there. Okay, and again, this is where you might think like, oh, I can make a double bond with one of these fluorines and borons. No, boron's an exception. It's going to stay just like this. It only needs those 3 bonds around it, and it's stable with just the 6 electrons. Okay, so again, beryllium and boron, 2 that are going to be electron deficient in terms of our exceptions. All right, a bigger group are our expanded valence shells. So this is when the central atom expands its valence shells to form additional bonds, which releases additional energy, which ends up being favorable, which is why this happens. So the central atom can hold more than 8 electrons. Now, really important is that this occurs with nonmetals from period 3 or greater. Higher meaning period 4, 5, or 6. So if I'm looking at my nonmetals side over here, here's 1 and 2. This will never happen with carbon, nitrogen, oxygen, and fluorine. We're only looking at this group going down, which is like our silicon and phosphorus, sulfur, chlorine, and then some of our other nonmetals down here. Okay, this is due to the fact that they have d orbitals available, which they will eventually learn can hybridize those to create these additional bonds. Okay, so again, this is going to be very specific, and this is where electron counting I think really helps students keep track of like some of these exceptions. So if we look at here where we have phosphorus, pentafluoride, phosphorus has 5. I have 5 fluorines. They each have 7. So 5 times 7 is 35, and 5 is 40. So I'm going to start with phosphorus on the outside. I already know this is an expanded octet because I already see that there's 5 fluorines attached to phosphorus, so it's got to have more than just the 8. So I'm going to spread out those fluorines as best that I can. And once we get into shapes, you'll start seeing where some of my shapes are coming from. I'm going to start with single bonds to all of them. So that gives me 2, 4, 6, 8, 10. So if I take out my 10, I have 30. So if I look, I have to get 6 onto each of these. Oh, no, I got 40. Okay. So I need 6 here. So if I think of 6 times my 5, I get to 30. So this will be 6 onto each of these fluorines, which is going to get me to my 30 there. Yeah, so 6 or 12, 24, and 6 is 30. All right, so that would be my structure there. Phosphorus has this expanded octet. That's okay. It's in period 3. It has d orbitals it can access, so this is a possible structure. All right, we're going to go diagonal in this chart here, and we're going to look at this one where we have chlorine. Oh my goodness, I'm getting so exhausted today. So I have my chlorine and my 3 fluorines here. So I have chlorine, And then I have my 3 fluorines, and they each have 7. So 7 times 3 is 21, plus the 7 is 28. I'm going to start with chlorine here, and I have my 3 fluorines. Now, when I start to draw these, I'm going to actually look at if I have any lone pairs to start. I know I'm going to have my 3 fluorines. They're going to have single bonds to them, and they're going to need 6 electrons each. So when I'm doing this, I'm going to kind of, let me start off with my fluorines actually. I'll just put them 3 around here. So 2, 4, 6 gives me 22. I know that I'm going to have 6 around each. So that's 2 or 6, 12, 18. So when I subtract out 18, I have 4 left. So I know I'm going to have 2 lone pairs on my chlorine. That's going to be important when we get into the shapes. For right now, I'm just going to put my 6 on these fluorines. Okay, and then I'm going to add on those 4 electrons. So I'm just going to put them right here. Okay, and that's okay. Chlorine is in period 3. It has its d orbitals. It can make this expanded octet. And again, this is where adding up those electrons helps me to determine that this actually has these 2 lone pairs on it. And this would be the acceptable shape there. Okay. All right, another one we're just going to do quick is the one in the bottom corner. So xenon is a noble gas, but some of our really large noble gases can react with something like fluorine, which is highly electronegative. So this is actually possible. So just be careful adding up valence electrons because xenon's going to have 8 valence electrons, 2 times 7 for those 2 fluorines. So 2 times 7 gives me my 14 plus my 8. So I have 22. So I'm going to have Xe. And I'm going to have the fluorines on the outside. I'm going to draw single bonds to them. So that's going to be -4, which gives me 18. I know I need 2 or 6 and 12, which means I have 6 electrons left. So I'm going to go ahead first so I don't forget, put those around my fluorines. So those 6 are actually all going to go on to xenon. So I'm going to put 2, 4, keeping them in pairs, 6. Okay, and again, I know this is okay. Xenon is in period 5. It has d orbitals that it can use to make this expanded octet, in this case, to form this molecule. Okay, so again, counting electrons, keeping stuff very organized is going to help you with these expanded octets.